Welcome everybody to the Jyväskylä Summer School. And the topic for today is going to be superconductivity in two-dimensional van der Waals materials. So, of course, if you have any questions, please don't hesitate of interrupting me during the talk. And as I mentioned yesterday, the more questions, the better. And again, every single question is welcome. So anything that comes to your mind, please let me know. So the schedule for today is going to be very similar to yesterday. So we will have first a 40 minutes of discussion about the two-dimensional van der Waals materials with superconducting order, then a 50-minute break where you can go outside, and I will also ask you something to think about, then 40 more minutes, then 15 minutes break, and I will also ask you something else, and of course you can also take some air, and then at the end we will have 40 more minutes. So the plan for today is two-dimensional superconductors, as I mentioned before, and in particular van der Waals superconductors, both intrinsic and also artificial superconductors. And first, to put just everything in place, we are going to review what is the impact of superconductivity on electronic structure, and in particular, what is the theoretical description that we will use to understand the electronic structure of superconductors. Then afterwards, we will start looking at both conventional and unconventional superconductors, and what is the difference between a conventional superconducting order parameter and unconventional one, and which different unconventional superconducting order parameters we have. And then afterwards, we will look at what is the impact of impurities in different two-dimensional superconducting orders, including non-magnetic impurities, magnetic impurities in conventional superconductors and both unconventional superconductors. And then at the very end, we will see how certain unconventional superconductors realize topological superconductivity, which is a superconducting order that also has topological order, and in particular, what are the consequences in terms of topological excitations in these unconventional superconductors. All right, great. So today we are going to focus on different two-dimensional materials. And just to, let's say, give you some reference of which materials we are going to talk about, let me just mention that the different types of superconducting orders that we will address appear in different types of van der Waals heterostructures. They appear first in just two-dimensional materials that are intrinsic superconductors, such as niobium diselenide or tantalum disulfide. So these systems are just one monolayer, and you don't have to do anything to them to make them superconducting. So they are intrinsic superconductors by themselves. And these monolayer superconductors, they are usually conventional gap trivial superconductors. So maybe the most common and perhaps simple type of superconductivity that we find in nature, that is just phonon-driven full gap in the Brillouin zone. But we will, of course, go to the details later on. Then other types of superconducting systems that appear in van der Waals materials, they only emerge when you combine materials that are not superconducting by themselves. And a typical example of this is graphene multilayers, and in particular, twisted graphene multilayers and also aligned graphene multilayers. So in these materials that are made of just different layers of graphene that you put on top of another, if you just look at one layer of graphene, you don't have superconductivity. And mainly because since it is a Dirac semimetal, you have a very, very low density of states at the Fermi energy, and therefore you don't have enough electrons to get to a superconducting order. But once you start stacking them together, and in particular twisting them or putting them on top of substrates, you modify the electronic structure enough so that a superconducting order may appear. And the superconducting orders that appear in these graphene multilayers and twisted graphene multilayers can be very, very different. You can have superconducting orders that are in principle conventional superconductors, so that they are compatible with a conventional S-wave superconducting order, but you can also find very, very unconventional order parameters. And let me just emphasize two of them. So first of all, if you probably heard about superconductivity before, and one of the things that we usually hear is that superconductivity does not like magnetic fields. And in particular, if you apply a magnetic field to a superconductor, you usually destroy it. That is true for some superconductors, but not for all of them. And in particular, there's a special type of superconductivity that it's called spin triplet superconductivity. It's a ferromagnetic superconductivity. It's a superconductivity that it's compatible with magnetic order. It's a superconductivity that if you apply a Zeeman field, and for a two-dimensional material, for example, an in-plane magnetic field, you actually do not destroy, but you may actually even enhance. And this superconductivity is very, very, very rare in nature. So it appears in some heavy fermion materials, some materials that have rare earth compounds and condo physics, and yeah, maybe some isolated material, but that's all. The very inspiring idea is that in these twisted van der Waals multilayers, and in particular in twisted graphene multilayers, signatures of spin triplet superconductivity have been observed. So superconductivity, that when you apply a magnetic field, it gets enhanced. And this is usually called reentrant superconductivity. So what usually happens in these systems is that you have different superconducting orders that compete. You have a conventional superconducting order that it's, let's say, very sensitive to magnetic field and that it gets destroyed by a magnetic field. And then you also have unconventional superconducting order, in particular spin triplet superconducting order. And as you apply a magnetic field, you start from a superconducting order that is conventional. This conventional superconducting order gets killed by magnetic field, but if you keep applying more and more magnetic field, suddenly your system becomes superconducting again, just because this spin triplet superconducting order gets enhanced by magnetic fields, and it's compatible with Simon fields. So that is one of the superconducting orders that we are going to address today, spin triplet superconductivity compatible with paramagnetic ordering. And then the other one, that it's also an unconventional superconducting order, and that appears also in some twisted graphene multilayers. It's a nodal superconducting order. So nodal superconductors are just superconductors in which not all the electrons in the Brillouin zone have a superconducting pairing. So some electrons do, and others don't. And as we will see later on, this actually means that the superconducting pairing matrix just has nodes in the Brillouin zone. It has some points in the Brillouin zone, which it becomes 0, usually for symmetry reasons. And let me emphasize that nodal superconductors, they are actually not that rare in nature, and they are very, very common. So if you think about many of the high TC superconductors, so cuprate superconductors, many of them, and I can even say most of them, are actually nodal superconductors. In particular, they are D-wave superconductors, but they show nodes. And then the third type of superconducting materials that we are going to focus on are unconventional superconducting materials that one makes unconventional just by combining with magnetic materials. So you can start, for example, from a two-dimensional magnetic material that is superconducting by itself. For example, now you're in diselenite, and now what you do is you approximatize this two-dimensional superconducting material to some other two-dimensional material, and by this proximity effect, you force the 2D material that was already superconducting to an unconventional superconducting order. And a typical way of doing this is by taking a two-dimensional magnetic material that is going to create an exchange field on the two-dimensional superconductor, proximatize the conventional superconductor to the 2D ferromagnet, and with this engineer an unconventional superconductor. So the key point here is that these different superconducting orders are described with the very same formalism. So we are going to solve the very same Hamiltonian to understand all these different conventional and unconventional superconductors. And the only difference between these different superconducting orders is just what is our single particle dispersion, whether if it breaks time reversal symmetry or not, whether if it has spin orbit coupling or not, and what is more important, what is the symmetry of the superconducting matrix in momentum space or in real space. So you can think that the superconducting order is just a new type of hopping. It's just a hopping that doesn't have creation and annihilation, but two creation and two annihilation. But we will go to the technical details later on. All right, good. So that was everything that I want to tell you about the different van der Waals materials that we are going to focus on. And now let me give you a reminder of where superconductivity is coming from and what is the fundamental ingredient for having superconductivity. So superconductivity is a symmetry broken state. It's a state that breaks a symmetry that your Hamiltonian originally has. And these symmetry broken states usually appear because of interactions. So you start with a Hamiltonian that has all the symmetries. And then when you apply a mean field approximation, then the mean field solution breaks the symmetry of your system. This happens for ferromagnets, antiferromagnets, and any kind of magnetic system that breaks universal symmetry. This happens for systems that develop charge density wave that break the original translational symmetry of the crystal. And this happens also for superconductors, in which your superconducting order breaks something that is called gauge symmetry that we are going to address now. So the basic idea is that for most of the emergent states, emergent electronic states in two-dimensional materials, we start from a Hamiltonian that has both single particle dispersion and interactions. And if we are in a regime in which we can apply mean field theory, and in the case of superconductors, we are going to assume that we are in that regime, then we can transform this Hamiltonian that has both bilinear and biquadratic interactions onto a Hamiltonian that just has bilinear interactions. They can be creation and annihilation, or two creation and two annihilation. So in this superconducting regime, we are always going to assume that we can define some single particle dispersion with normal and anomalous terms, but that we can treat it with mean field theory. And as I mentioned yesterday, of course, this is not the case for every single correlated state. And let me emphasize that there are some correlated states and even maybe some superconducting states that perhaps cannot be understood with mean field theory, and that may require a conventional full many-body treatment. We are not going to focus on those today, but let me just emphasize that they do exist, and there may be some superconducting orders that you cannot understand in this way. All right, great. So now, before we move on to the different types of superconductivity, let me emphasize why superconductivity is one of the most central ideas in condensed matter and in quantum materials, and of course, in two-dimensional materials. So if you think about the different, let's say, emergent phenomena in nature, in particular, what is the most robust phenomena in nature, I think that it's worth saying that superconductivity is one of them. So if you think about how you measure microscopic quantity, so the most microscopic, let's say, constants in nature that you may imagine. So for example, the charge of the electron and the Planck's constant. Of course, the first idea that comes to our mind is that if you want to measure the charge of the electron, maybe it's idea to just take one electron and measure it somehow. This is, of course, a fair idea, and you can get an estimate of the charge of the electron in that way. And if you want to measure the Planck's constant, well, maybe you should take the smallest quantum system that you can, the most isolated one, the smallest one, and try to see the Planck's constant from that smallest system. What is actually the reality is that the most precise measurement of the charge of the electron and the Planck's constant involves not measuring a single electron and not measuring a single quantum system, but actually taking billions and billions of atoms and electrons, putting them together and exploiting an emergent phenomena that you get when you put all these different quantum particles at the same time. So in particular, when you get a superconductor, you essentially have a system that has a macroscopic collective many-body wave function in which you get a quantization of the flux. So you take a superconductor, you thread a flux or a magnetic field through a hole that the superconductor has, and due to the properties of the many-body wave function of the superconductor, essentially you are constrained to put a flux that is quantized exactly in terms of the Planck's constant and the charge of the electron. So just by measuring this magnetic flux, you know what is this ratio in a system that has billions and perhaps even trillions of electrons. Now, there's another quantum state and another emergent phenomena that also realizes a very similar phenomenology. And this state is the quantum Hall state, which is one of the simplest topological states that we find in nature. So the basic idea of the quantum Hall effect is that you have a system in which the conductance is quantized in terms, again, of the charge of the electron and the Planck's constant. And this quantization is extremely perfect. It's perfect to many, many digits. So I don't remember exactly the number, but you get actually the most precise estimate in nature of this ratio. So just by combining measurements in two different quantum materials, superconductors and topological insulators, you get the most precise estimates of the charge of the electron and the Planck's constant. And I think that these are two of the most beautiful examples of emergence that we have in condensed matter. So we get a phenomena that is nearly perfect, even though we have an extremely complex system with, let's say, with particles that we may not even fully, let's say, understand, or that we may not be fully able to treat exactly. So this quantization of flux and this quantization of conductance is completely independent on any small details that your material may have. It doesn't depend exactly on the electronic structure that you have. It doesn't depend exactly on what is the, let's say, crystal structure that you have, or if you have some impurities around, or if you have a little bit of strain here and there. It is phenomena that is resilient to any perturbation. All right, so this is everything that I wanted to tell you to motivate why we are looking at van der Waals superconductors, and in particular at superconductivity generically. So now let us move on and see how we are going to describe superconductivity from the point of view of mean field theory, from the point of view of the electronic structure that two-dimensional materials develop. So the basic idea is that every time that we have a superconductor, we always need to keep in mind that this superconductivity is going to come from some interacting Hamiltonian, some Hamiltonian that has both single particle dispersion and some interacting term. And in general, we may not know what is this interacting term, and perhaps what is most importantly, we may not be even able to solve this interacting term. But for us, the only thing that is important is that it does exist, and it's going to have some mean field Hamiltonian. So for superconductivity, what is usually important is that this interacting term leads to some attractive interaction somewhere in the Brillouin zone, close to the Fermi energy. You may have both, let's say, repulsive interactions and attractive interactions, but to have superconductivity, it's important to have some residual attractive interaction somehow. And let me emphasize that this doesn't mean that electrons need to attract themselves via Coulomb interaction, because they don't. They have opposite charges. What this actually means is that the effective interaction between them has to be attractive in at some distance, at some momentum, and this can actually happen directly from repulsive interactions, as we will discuss later on. So the basic idea is that for electrons to attract each other, one can think about many, many different mechanisms. And let me emphasize just two main groups of mechanisms. The conventional mechanism, that is the one that it was originally proposed for superconductors, and that is capable of accounting for superconducting properties of conventional superconductors, is electron-phonon coupling. So here, the basic idea is that electrons attract each other, not through Coulomb interaction, because it's in principle repulsive, but rather through some other particle. And this other particle is a phonon. This other particle is just a deformation of the lattice. So the basic idea is that one electron goes through the lattice, deforms the lattice, and this deformation of the lattice, it's effectively attractive to another electron. This electron-phonon mechanism is perhaps the most well-understood mechanism for superconductivity. And it is fair to say that it allows to make a faithful prediction of superconductors that are driven by electron-phonon interactions. So, for example, critical temperatures of superconductors that are driven by phonons can be well estimated with advanced theoretical tools such as density functional theory, for example. So all these types of superconductors are not all, but some. Aluminium, you can estimate. Well, yeah, for example.
You know what it is.
Yeah.
There is an issue. There is one part. It's actually the phonon is kind of like the Coulomb interaction, direct.
Yeah, of course, the direct Coulomb interaction is a problem. So, all right, let me phrase it in this way: is the mechanism that we understand the best, and it's the mechanism that we can, in which we can make the best predictions for critical temperatures. I think that that's a fair statement. So, let's say conventional materials that are superconducting, that are, let's say, metals that at very low temperature become superconductors, they are usually driven by electron-phonon interaction, or most of them. Then there's a second group, which is the group of unconventional superconductors. And in these unconventional superconductors, what we believe is that the mechanism that drives the attractions between electrons is not electron-phonon, or it doesn't have to be electron-phonon, but it can be any other quasi-particle. So as you know, in quantum materials, in two-dimensional materials, we may have many different types of quasi-particles. So we have magnetic order, we have magnons, they can be ferromagnetic magnons or antiferromagnetic magnons. Of course, if we have a metal, we also have plasmons. You have a system that in which two valences compete, we can also have valence fluctuations. If we have a system that has a charge density wave order, we can also have charge density wave fluctuations and so forth. And all these types of fluctuations are actually quasi-particles. They are, let's say, particles that emerge in the material and that in principle have a frequency momentum relation. And all these quasi-particles, in principle, they can mediate superconductivity. All these quasi-particles, in principle, they can be the mediators of an attractive interaction between different electrons. So for unconventional superconductors, what we believe is that some of these quasi-particles are the ones responsible of superconductivity, and phonons are not so much responsible of this. The biggest challenge of unconventional superconductors is that theories for estimating superconducting transition temperatures from these mechanisms are much less understood, and they have a much smaller predictive power. So whereas superconductors with electron-phonon interaction, we can predict them up to a certain degree, unconventional superconductors driven by any of these mechanisms are way more challenging, and it's extremely difficult to even know what is the mechanism that it's at play in different materials. So from our point of view, we are not going to worry so much about which one is the mechanism that matters for us. Maybe electron-phonon, maybe let's say magnon interactions or plasmons and so forth. What's important is that there's some particle somewhere in the material that somehow creates an effective attractive interaction. And that will be our starting point, an effective attractive interaction mediated by some of these quasi-particles. All right, great. So then let's start with the simplest interacting Hamiltonian that we already discussed yesterday, which was a Hamiltonian in which we introduce the minimal interactions that we can introduce in a model, which are just on-site interactions. So electrons in the same place attract each other if we choose a value of u that is smaller than 0. So we just have interaction between electrons in site I with a spin up and electrons in site I with spin down. And as we discussed yesterday, this model alone allows you to realize both superconductivity and magnetism. And today, since we are talking about superconductivity, we are going to focus on the case of u smaller than 0. So the basic idea is that we have this interacting Hamiltonian, and we use our mean field approximation we discussed yesterday. And when we take expectation value between two creation and two annihilation, we essentially get an order parameter that multiplies terms in the Hamiltonian that are no longer creation and annihilation, but two annihilation and, of course, two creation. And this is essentially what we will call a superconducting term. It's a term that has two annihilation and two creation. And let me just mention that this is maybe the simplest superconducting order that we can think about. It's an S-wave superconducting order, a superconducting order that it's uniform in momentum space when we do the Fourier transform. And it is the superconducting order that accounts for several materials that are driven by electron-phonon interaction, for example. All right, so before we start solving this Hamiltonian, let's just try to understand what this term actually means, and in particular, how it modifies our Hamiltonian and how it breaks symmetries in our Hamiltonian. So right now, we are going to focus on Ci up, Ci down, but let me emphasize that what is important of this argument is that you have two creation and two annihilation. So later on, we are going to start putting different indexes, different spins, but this argument is going to also apply in that case. So the basic idea is that if you consider this term in the Hamiltonian and you start thinking about what is the many-body ground state that it's compatible with that term, you actually reach an interesting conclusion. So this term in the Hamiltonian essentially destroys two electrons or creates two electrons, right? So CC destroys two, C dagger creates two electrons. So now if you think that you have a many-body ground state of your Hamiltonian, that by definition is the state with the lowest energy, then the conclusion that you reach is that actually this state cannot have a constant number of electrons, just because if you have n electrons, when you apply the Hamiltonian to your state, you get a linear combination of n minus 2 and n plus 2. So a many-body wave function with a constant number of electrons, in principle, it's not an eigenstate of this Hamiltonian, but you need to consider a wave function that somehow has at the same time 2 and 4 and 6 and 8 and 10 and so forth, so that when you apply this term, you likely go to the same state that has either still an even number of electrons or an odd number of electrons. So what is important for superconductivity is that the many-body wave functions have a fluctuating number of electrons, but the parity of the number of electrons that you have is conserved, just because you have here, let's say, 2 creation operators or 2 annihilation operators. And this is going to be important when we discuss about topological superconductors later on. So for us, let us just remember that in a superconducting system, or in a system that has a superconducting order somewhere, we can have ground state even number or with odd number. All right, great. So that is one of the things important to remember about superconductivity, and the other one is actually very much related with that fluctuating number of electrons. So any symmetry that we have in condensed matter can be written in terms of an operator, right? And in particular, an operator that modifies the creation operators and the annihilation operators. So in particular, if you think about, let's say, translational symmetry, the only thing that you have to do is to transform Cn into Cn plus 1, for example. If you think about time reversal symmetry, you have to switch up by down and put complex conjugate in an I somewhere. And then if you think about a symmetry that we call gauge symmetry, we just have to transform our original creation operators into creation operators times a phase and annihilations with the opposite phase. So this gauge symmetry is essentially the symmetry that we usually say that all the wave functions have. So when we talk about a wave function, we usually say that phases of a wave function are not important. The only thing that it's important is differences in phases. So we usually say that any observable needs to depend on the square of the absolute value of the wave function, not in its specific phase. And the phase only appears when you do interference. But in that case, you do not even see the phase. What you actually see is phase differences. So that gauge symmetry, when you go to second quantization, just takes this form. And what is actually very interesting to note is that any type of conventional term in your Hamiltonian, such as hopping or magnetic ordering or spin orbit coupling or interactions, respects this symmetry, right? So every time that you have as many creation as annihilation, these two phases just cancel out. And when you do a gauge transformation in the Hamiltonian, your Hamiltonian remains as it was before. So gauge symmetry is a symmetry of all the Hamiltonians that have hopping or magnetism or spin orbit coupling or any kind of interaction and so forth. But that is not the case if you have superconductivity, right? Because if you have superconductivity, actually, you have terms that have 2 creation or 2 annihilation operators, right? So when you do a gauge transformation, the phases don't cancel out, but they actually add to each other. So in other words, the superconducting order is an order parameter that changes when you do a gauge transformation, in the same way that a magnetization changes when you rotate in space, right? So if you initially have magnetization in the z direction, if you rotate your reference axis, then it becomes in some other direction. So the superconducting order transforms in the very same way, but just under this gauge transformation that in principle, it is a transformation that we thought that every single wave function should have. So this is essentially one of the important ideas for us, that superconductors break gauge symmetry. And this is actually extremely important for understanding many of the phenomena in superconductors. So for example, the quantization of flux, it's a direct consequence of this breaking of gauge symmetry. The Josephson effect, that it's one of the most important effects that we have in superconducting devices, is also a consequence of this breaking of gauge symmetry. And even you can think that the supercurrents in superconductors up to a certain degree is a consequence of this breaking of gauge symmetry. So we are not going to, let's say, dive into supercurrents or Josephson effect, but let me just emphasize that all of them are very much related with this symmetry breaking. All right, great. So now we understood what is the mathematical form of a superconducting term in the Hamiltonian. So let us now see what is the impact that it has in the electronic structure. In particular, how do we have to modify our formalism to account for superconductivity. So let's just start with a Hamiltonian that has both kinetic energy and a superconducting term. And let me just write this in reciprocal space to be a little bit easier. So if you didn't have superconductivity, this would be just the electronic dispersion in a reciprocal space. So the bond structures that we were discussing yesterday. And now if you want to add superconductivity, you just have to add essentially this term, which is the Fourier transform of the term in real space that we wrote before. And let me just note that while this has kk, this has k minus k. And this comes from the fact that you have, let's say, two creation operators. So now what we have to do is we have to diagonalize this Hamiltonian, that it's not diagonal once we add the superconducting term. So if we didn't have superconductivity, the Hamiltonian would already be diagonal in this basis, right? Because we just have c dagger k ck, but since now we have ck c minus k, now it's no longer diagonal, right?
If there were no questions, I will add one. The k minus k aspect, you said that it's because you have two operators. Can you elaborate on it?
Oh yeah, that's a good point. So let's go back to the superconducting order here, for example. So if you do a Fourier transform, you essentially replace this ci by something like sum over k e to the I k n, let's say cn, or yeah, ck. Then, yeah, I think it's better if I write it. Yeah. So you have a term in your Hamiltonian that looks like this, right? So Cn up, Cn down, and now you want to Fourier transform this. So you say that, well, the Cn is replaced by something that looks like e to the I k n ck down, and then the Cn up, and then the Cn down gets replaced by something that is e to the I k prime and ck prime down. And now you have to essentially make this whole sum, right? And let's also put here sum over n so that things are easier for us. So now in this sum, you can reorder everything in any way, right? Because this is just an infinite sum. So the basic idea is that you can pick first this term here and this term there. And you can think about what this sum actually gives rise to. So this kind of summation is just a delta function, right? So it's just a function that is going to be 1 or infinite, depending how you define it, when this is 0, and it's going to be 0 in any other case. What this actually means is that this summation is going to put k prime equal to minus k, essentially, in this summation. So when you perform the whole summation, you essentially end up with something that looks like ck up and c minus k down, right? So this is where the minus comes from, because for this term to be something finite, this up here needs to be 0. Let me emphasize that if you had daggers here, for example, then you would introduce here a minus, you would introduce here a minus, and therefore it would remain plus. So that's why you have a minus there. Yeah, thanks. That was a very good point. All right, great. So now we have to diagonalize this Hamiltonian up here, right? And actually diagonalizing this Hamiltonian is very, very easy if you know what is the trick. So the trick is actually to define new operators, and in particular new field operators that are what we call a Nambu spinner. So this essentially, this is a column vector in which the first element is ck up, then ck down, then c dagger minus k down, and the minus c dagger minus k up. And let me emphasize that this minus here, you can change it. So this can be minus, this can be plus. You can put any phase here that you want. The only thing that it's important is to be consistent when you choose a basis. But taking this minus usually makes things easier in terms of superconducting order. So let's take the minus. So now the basic idea is that once you define this Nambu spinner, you can try to rewrite this Hamiltonian in terms of this new field operator. So if you think that this is, for example, an scalar, so well, or at least the matrices that multiply your field operators here as scalar, if you define this psi k as a vector, then this H is going to be a new matrix, right? So if this is a vector with 4 components, this H is going to be now a 4x4 matrix. So, for example, if you take this Hamiltonian and you define your Nambu spinner in this way, where in the Nambu spinner we say that this is the electron sector and this is the whole sector, then the form of H that you have to write down so that you recover this form of the Hamiltonian is essentially this one. And let me emphasize a few things in this Hamiltonian. First of all, the upper left corner is the electron part of the Hamiltonian. The lower left corner is the whole part of the Hamiltonian, namely that this term, when you, let's say, multiply this matrix by this Nambu spinner, essentially gives rise to the normal terms in the Hamiltonian. So the Hamiltonian that had C dagger and C. And the same for the low corner, so for the part of the matrix that it's in the bottom right. So this also gives rise to C dagger C terms. And now notice that there's a minus sign in this matrix, and this just comes from the fact that here you have daggers, and when you multiply, you are essentially switching dagger by non-dagger that introduces a minus sign. And then, of course, you need to have the superconducting term somewhere, and this somewhere is essentially in the off diagonal. So something important to notice of Nambu spinners is that somehow you kind of doubled the degrees of freedom that you have now, right? So if you first had just one electronic dispersion, now you seem to have 2 electronic dispersions, right? And these 2 electronic dispersions are coupled to the superconducting order. And this is something that is going to appear in every single electronic structure for a superconductor. So let's see just a very specific example, and let's take maybe the simplest die bonding model in 2 dimensions that we can think about, which is a single orbital model in the square lattice. So if we have a single orbital in the square lattice, we essentially have a single band, right? That it's a cosine-like band. And now we can put the chemical potential somewhere. So let's put it here, for example. This is the electronic structure that we have if you just have a conventional Hamiltonian without superconductivity. And you can think that you have both up and down spins that are just degenerating in energy. Now we set up the Nambu spinner. So we add a superconducting term, but to start with, let's start with delta equal to 0, exactly. All right. And when you just rewrite this Hamiltonian with delta equal to 0 in your Nambu basis, you get a doubling of the degrees of freedom, right? Because you now no longer just have the dispersion of the electron part of your Hamiltonian, but you also have the holes, which were kind of the 2 components of the Nambu spinner that were in the bottom. So here in this band structure, the red bands are essentially the electron part of your Nambu Hamiltonian, or the Vaucluse of the Jens Hamiltonian, and the blue one is essentially the whole part. And again, red and blue are just, this is red, and this is blue, right? So essentially, the blue part is kind of the red one reflected because of this minus. All right, good. So this is in the absence of superconductivity. So we kind of set up a Nambu spinner to solve the Vaucluse of the Jens Hamiltonian that has a superconducting term that is exactly 0. It seems a little bit, yeah, funny, but let me just tell you why this is actually illustrative. So now let us take delta different from 0. And when you take delta if different from 0, what actually happens is that these 2 bands that initially crossed, that were the electron band and this whole replica, now they anti-cross. And this anti-crossing is essentially proportional to the superconducting gap that you have in your Hamiltonian. So the bigger you make this delta in the Hamiltonian, the bigger this gap becomes. So in other words, a superconducting order in a Hamiltonian essentially opens up a gap in your single particle electronic spectra, at least an S-wave superconducting order that is uniform in momentum space. So when we deal with superconducting electronic structures, we are all the time going to think about this Bogoliubov-de Gennes structure that has a hole part, an electron part, and where superconductivity essentially gives rise to anti-crossings between electron bands and hole bands. Yes?
What does the green color mean? A red electron to holes from the anticonductor, no green?
Yeah, that's a very good question. So when you have superconductivity, your Hamiltonian is no longer block diagonal, but you now have terms in the off diagonal. So what this actually means is that these wave functions here, they are not electron and they are not hole, but they are something in the middle. So the color scale here is essentially blue is hole, green is something in the middle, red is electron. So what this actually means is that this wave function here, right here, that is green is 50% electron and 50% hole.
It's a big magenta or something.
Yeah.
It's a mixture of yellow.
Yeah, that's right. The color scale should have been magenta there. Yeah. Yes. So what is the relation? Yeah, so the bigger the superconducting order is, the bigger this gap is. So this gap is essentially proportional to delta. So if you, yeah.
They are not equal, right? The water from one gap then.
So this gap here is essentially just delta or 2 delta, depending on how you define it.
Okay, it's not the water.
I mean, it's also the order parameter, right? So this delta is.
Definition of this two.
So let's say if you define the order parameter as, of course, it depends how you define it, but this is interaction times expectation value of CC, for example. So this is kind of the superconducting gap. Now, if you define your superconducting order just as the expectation value, then of course you have a coupling term missing.
Yeah.
But let's say this delta is, for example, the delta that one sees in spectroscopy. So when you see a gap in a superconductor, you're essentially seeing this exact delta. But not the expectation value alone, but the expectation value times the coupling constant would essentially impacts the electronic structure. So
Value has different dimensions. Pairing up to the value. The dimension
yes, dimensionless. Yeah, exactly. So let's say your observable is delta, or the absolute value of delta.
Yeah.
Let's say.
So I need to tell you that I feel like there is a conceptual thing. Like this guy introduced the electrons and holes without having solved the event structure. How can we talk about electron and hole sectors in Hamiltonian without do we already know and would you give us a basis? But normally we solve and then we see the dispersion that we can talk about in dispersion.
Yeah, that's a really good question. So let me first mention that when I say electrons and holes here, I am not referring to electrons and holes in a semiconductor. So in a semiconductor, we say that electrons are something that have a, let's say, parabolic dispersion like this, and holes a parabolic dispersion in the other direction. So these electrons and holes are completely different. So let me rephrase this as particles and antiparticles, for example. So this is the particle sector. This is the antiparticle sector.
But
yes, you can phrase. Yeah, exactly. You can phrase it in that way. And for example, if you think about electrons and holes in a semiconductor, both electrons and holes in a semiconductor are here. Let's say are in the particle sector. Let's say.
The important thing is to notice that actually cepsilon K contains mu at 10 of 10.
Yeah.
So actually this is normal dispersion minus 10 of 10. So you expand around 10 of 10. So the result will actually differ on depending on the field.
Yeah, of course. And I mean, you can even have, let's say, several pockets coming from here. So you don't have to even have just electrons. You can have both electrons and holes.
Definition of electron and hole will depend on where
Yeah, but you can think that this is just a kind of a mathematical trick, right? So this is just kind of a way of rewriting your Hamiltonian by redefining your field operators. Yeah, and I think that there was a question in the chat.
About divergence, but I
Oh, yes. So we will see the difference between S wave, D wave, and so forth later on. All right, great. So essentially, when we have superconductivity, we open up a gap in the electronic dispersion, and this gap that you see here is the gap that one sees in transport experiments in the tunneling regime. So if you take a superconductor and you couple another metal very weakly, it can be an STM, it can be another metallic contact, then what you actually see is that there's a gap in your system, and that gap is essentially this delta over here. All right, great. So now let us just look at several superconducting systems with S-wave superconductivity and see if they are the same, they are different, if there's some substantial difference between them. So for example, let's just take a triangular lattice with different chemical potentials. So the difference between, let's say, this band structure and this one is this, and this one is that I am changing the chemical potential. So in one, you can even go from electrons to holes as you change the chemical potential. So for example, here you would have holes in a semiconductor, right? Because this dispersion goes down, whereas here you would be in the electron sector, or in the electron part of your semiconductor, let's say. Now, if you add superconductivity, you open a gap in this one, in this one, in this one, and actually in every single case. And if you take the same delta for all, the gap is exactly the same. What this actually means is that no matter how your electronic dispersion is, no matter where your chemical potential is, if you have a superconducting order, you always open a gap. And if your superconducting order is uniform in momentum space, this gap is going to be exactly the same no matter what. All right, great. So now let's look at a different lattice, so a square lattice. So before it was a triangular lattice where we changed the chemical potential. Let's do just the same with the square lattice. And in the square lattice, again, we can go from being close to the top of the band to close to the bottom of the band. And now when we add superconductivity, we see essentially the same, that a gap opens up with the same magnitude, no matter where the chemical potential is, no matter what is the dispersion of our system. So superconducting S-wave order always opens a gap, irrespective of the electronic dispersion. And if you have even a superconductor that has many, many bands, it's also going to open gaps in every single band. And that is something that you will do during the exercise sessions. All right, great. So before I was talking all the time about S-wave superconductivity, right? About a superconducting order that it's uniform in momentum space. What we are going to do in the next part of the lecture is to think about other superconducting orders that can have a much more complicated structure in momentum space, and in particular, that can give rise to a superconducting gap that may even change signs in momentum space. So just to motivate that, let me just show you here one case of a nodal superconducting order. And a nodal superconducting order is just a superconducting order that in some parts of the Brillouin zone is non-zero, and in other parts of the Brillouin zone, it just becomes zero. So it's no longer uniform. So for example, if you take a triangular lattice or a square lattice and you add a nodal superconducting order, at this stage is not very important which one it is. What you actually see is that a gap opens up in some parts of your Brillouin zone, as it happened with an S-wave order parameter. But then there are other parts of the Brillouin zone where no gap appears. So your bands just remain as they were before. Oh, and let me emphasize something that I didn't mention, is that all these bands that I'm showing you here are just the electron part of your Hamiltonian. So this is just the projection on the electron sector. So I am not showing you the whole sector anymore. So you see that in some parts it opens a gap, in others it doesn't. And the magnitude of the gap, now it depends on where your chemical potential is. So for this chemical potential, it seems very large. For this chemical potential, it seems very small, even though I'm taking kind of the same value in the Hamiltonian now. And of course, for this region, it's all the time 0. So let me first answer the questions in the chat. Yeah, so the first question is, how is the body of the James Hamiltonian different from phonon-mediated Hamiltonian? So as I mentioned before, the idea is that irrespective of what is the mechanism that gives rise to superconductivity, we essentially have Hamiltonians that look very much in the same way. And instead of thinking about what is the mechanism that promotes the superconducting order, we just think about how it looks like in reciprocal space. All right, great. So now let's think about, let's say, the electronic structures in 3 different cases. First, if we don't have superconductivity, we have S-wave superconductivity, and if we have this nodal superconductivity. So in the absence of superconductivity, we just have a metal, right? Now, if we have S-wave superconductivity, we have a gap in the full Brillouin zone. So essentially, when we compute the density of states, for example, we will see a full gap. And for a nodal superconductor, we have gaps somewhere in the Brillouin zone, but not in other places. And this nodal superconducting state is, for example, the case that I mentioned at the beginning, which some electrons get superconducting and others don't. Let's say, so these electrons here, they behave as if there was no superconductivity, because they are essentially the same as in the absence of superconductivity, whereas these electrons here behave as in the full superconducting case. And of course, this applies to, let's say, different types of structures. So the previous idea was in the square lattice, where we can have nodal order parameters, but you can play the very same game in the triangular lattice or in the honeycomb lattice or in any super lattice. And in all lattices, you can find both superconducting orders that have a full gap in the Brillouin zone and superconducting orders that have gaps only parts of the Brillouin zone. All right, great. So I think that now it's a very good time to take a break. So we will have something between 10-15 minutes, and I would say that we can aim at 15 minutes. So we can be back at around 10:08. And for the break, of course, you can go outside, have a drink, get some air. But if you also want to think about something, let me ask you this. So let's imagine that we have these very special superconducting orders that so far I didn't talk about. But my question for you is, which one of these 2 relations you think that is the right one? So the one on the right or the one on the left? And let me mention that the only difference is a minus sign between both of them. And this is going to be very important for what we are going to discuss. So yeah, see you in 15 minutes, so at 10:08.